So now we want to use additivity of moments to find a centroid of a region that's composed of two or more subregions. So if you've got a region that's composed of non-overlapping subregions, then the moment of that region is just the sum of the moments of the subregions. That's what additivity of moments says. So if R is R1 union R2, then the x moment of R, you just add the x moments of the two regions. And the y moment of the big region, you add the y moments of the two subregions. So let's put this to work here. So we want to find the centroid of our region here, not by integration, but by locating centroids of the rectangles and triangles and then using additivity. So notice here that we have one rectangle and one triangle that we're looking at here. And recall that mass is density times area for a lamina, and we're looking at centroid, so that means uniform density. We can take rho equal to 1, so this is just 1 times A, which is A. So mass and area are the same when you're finding centroid for lamina. So we've got this rectangle that is 3 by 3, actually a square here. So here mass is equal to 9. And then we've got a triangle here. We could consider this side to be the base, and then the height would be 2. So we got a base of 3 and a height of 2, so 1/2 times 3 times 2, so that's 3. So we got a mass of 3 here. And then we can find the centroids here. So the centroid of the rectangle, we've got some lines of symmetry here at 3.5 and 2.5. So that's going to give our centroid there. So 3.5 is our x. So that's 7/2. And then 2.5 is our y, that's 5/2. And then for the triangle here, our x bar, we have got coordinates here of 0, 0, and then 2, 1, and then 2, 4. So our x bar, we average the x coordinates, so 2, 2, and 0. So 2 plus 2 plus 0 over 3 is 4/3. And then the y coordinate of the centroid, average the y coordinates, 4, 1, and 0. 4 plus 1 plus 0 over 3, 5/3. So 4/3, 5/3. So 1 1/3, 1 2/3, about right here. So there's our centroid. So then x bar for the total region. By definition, x bar is the y moment divided by the total mass, which in our case, mass is area. So this will be the y moment divided by area, which is going to be 1 over the area. And then the y moment, you sum up the mass for each region, and then times the x coordinate of the centroid for each region. So our total area here was 9 and 3, 12, so 1/12. And then our mass here, again, mass is area for lamina. So we had area of 3 and then an x coordinate of 4/3. Let me go ahead and bring this down. So area of 3 times an x coordinate of 4/3 in the first region, plus an area of 9, or mass of 9, and then times the x-coordinate in that region, 7/2. So these 3's will cancel. So we get a 4 plus 63/2, and then times 1/12. And if we put that in the calculator, we will get 71/24. And then for y bar is the x moment divided by mass. And so this is the x moment divided by area again. So that's going to be 1 over mass, or 1 over area, and then we are going to sum up the individual masses times the y-coordinates of the centroids. So total mass is 12, so 1/12. And then we're going to do the mass of the triangle 3 times the y-coordinate, 5/3. Plus mass of the rectangle, 9. And then times the y-coordinate, 5/2. So these 3's will cancel again. And we put that in the calculator. And we get 55/24. So our centroid here for the entire region is 71/24, and then 55/24. And this is approximately 2.96, and this is approximately 2.3. So x-coordinate of 3, and then up to 2.3, about right here. So that is our balance point for this entire region of uniform density. So it didn't have to do any integration to get that. Additivity of moments here. So we're adding the mass of the region times the x-coordinate of the centroids to get the x-coordinate of the centroid of the total region, and then the masses times the y-coordinates of the subregions to get the y-coordinate of the centroid.